Imagine a steel bridge buckling under a massive load. Mapping every physical force creates a chaotic tangle of three-dimensional vector arrows. Tracking equilibrium using traditional Newtonian mechanics requires you to resolve the specific direction and magnitude of those vectors at every single point. For a complex, continuous geometry, the math becomes computationally overwhelming. To analyze these structures more efficiently, we can abandon directionality entirely. Instead of tracking thousands of individual forces, we shift to calculating unified scalar energy fields. A scalar is a pure magnitude, a single number. In structural mechanics, this value encapsulates the total state of a system without needing to resolve individual force directions. By evaluating energy rather than individual forces, the complex trigonometric requirements of vector mechanics disappear. The structural analysis converges into a single, comprehensive energy balance. To model reality efficiently, engineers trade the visual intuition of physical force factors for the analytical power of pure energy. The mathematical framework that utilizes this energy-based approach is known as Hamilton's principle. This is a systematic, rigorous rule. We use it to derive the exact equations of motion for any mechanical system. The principle is versatile, applying equally to dynamic impacts, such as a vehicle crash, and to static problems, like a stationary building frame. This principle functions as the foundational engine that makes modern finite element analysis possible. To use this tool, we must first categorize a structure's state into three distinct, measurable energy components. This provides the mathematical bridge needed to map the physical behavior of continuous materials into the discrete algebraic systems required by FEA. Consider a continuous structure, like a cantilever beam, subjected to a dynamic moving load. The first component of our energy anatomy is kinetic energy, denoted by variable T. Kinetic energy is a direct reflection of the physical motion and the mass distribution of the system. In dynamic problems, this term allows the math to explicitly account for the structure's inertia as it oscillates. We can draw velocity maps across the geometry to locate exactly where this kinetic energy is most concentrated. If the structure stops moving, its velocity becomes zero, and the kinetic energy component disappears from the calculation. Any physical motion or oscillation injects this kinetic energy into the mathematical profile of the structure. We then shift focus from the external movement of the structure to the internal resistance occurring within the material itself. This is the second component of the Hamilton functional, potential energy, denoted by U. While basic physics often focuses on gravitational potential, the mechanics of materials focuses on an internal energy state. In this context, potential energy is elastic stream energy. As the body deforms under load, the material stores energy, acting like a coiled spring. Mapping internal stress gradients visualizes exactly where this potential energy is trapped within the geometry. This stored energy exerts a constant force that attempts to restore the structure to its original, undeformed shape. A deformed structure is essentially a mechanical battery, defined by the quantity of its trapped elastic strain energy. The third energy component required is external work, denoted by W. The fundamental definition of work is a force multiplied by a displacement. Applied structural forces can be concentrated at single points or broadly distributed across a surface. When the specific point where a force is applied moves as the structure deforms, that force performs work. These massive external loads perform work by pumping energy into the system as the structure displaces under pressure. We combine these three components into a single expression for total structural energy: kinetic minus potential plus external work. The state of any structure is a continuous balance between its motion, its internal resistance, and these external driving forces. We can now move from the physical definitions of these energy components to their mathematical execution within Hamilton's functional. This dynamic equation states the time integral of the variation of total energy, T minus U plus W, equals 0. The delta variation operator tests all theoretical structural deformations. The system is evaluated over a specific period, moving from an initial to a final state. Out of every theoretical path the material could take, the true physical deformation is the one where this energy variation integrates perfectly to 0. This calculus expression functions as a foundational optimization principle, determining how any physical system settles into a state of equilibrium. For most finite element analysis applications, we apply a specific constraint. We focus on static problems. In a static problem, the structure has zero velocity. Because motion is zero, the kinetic energy term is removed. In a stationary system, time loses mathematical relevance. We remove the integral limits and time operator, stripping temporal dependencies. This leaves a simplified final expression. The variation of negative potential energy plus external work equals zero. This expression represents a direct balance between the internal elastic strain and the external work applied to the structure. By mathematically removing time and motion, Hamilton's principle provides the precise, minimized scalar framework that powers modern static finite element modeling.